Welcome to a new lesson of the Haskell course. In this one, we are going to cover Cabal, a common architecture for building applications and libraries, and the concept of language extensions. We are going to start with an introduction to Cabal. Then we're going to create a new Haskell project using the Cabal architecture. Then we're going to go over the folder structure and the Cabal file that has all the configuration necessary for building your software. And at the end, we're going to use Cabal to install and integrate an external library with our own code. After that, we're going to do a quick introduction to language extensions and pragmas. And as examples, we're going to modify our code to use NumericUnderscores and TypeApplications. Let's get started. This is the Cabal User's Guide. It has pretty much everything you might need to know about Cabal and more. We're going to use it a couple of times in this video to get you used to it. Cabal is the standard package system for Haskell. It helps us configure, build, and install Haskell software and to distribute it easily to other users and developers. It can be used to work with local packages or to install packages from online archives, including automatically installing dependencies. By default, it's configured to use Hackage, which is Haskell's central package archive that contains thousands of libraries and applications in the Cabal package format we're going to see today. If you follow the installing Haskell video, you should already have Cabal in your system. The first thing we are going to do is to update our index. If we search in the documentation, the command Cabal update, we see that Cabal update updates the state of the package index. In our case, by default, we use Hackage, so it will update Hackage's package index. So let's go to our project. This is an empty repository called ForestGame. So we are going to run Cabal update, hit enter. We'll have to wait for a bit. Awesome, our package list has been updated. As you can see, the index state is at almost June of 2023, which is today. Now we can start working with our actual project. To start a new project, we use the Cabal init command. I'm going to make it a bit bigger. And it's going to ask you a couple of questions. The first one is which type of package you want to build. A library for other people to use your code, or an executable, meaning like an app, both, or just a test suite. Of course, this is just an initialization thing. You don't need to commit to this for the rest of the project. You can just start as an executable and then change the files we are going to see next. This is just to bootstrap the project. So let's choose executable. Do you wish to override existing files? There's no files. Let's say no. Please choose your version of Cabal specification to use. This choice might be relevant in the future, but for now, let's stick to the default of 3.0. Package name, ForestGame is fine. Package version, the default one. A license, we can choose MIT. Author name, maintainer email. I have the default GitHub email, but I can use project homepage. There's no project synopsis. Project category. In this case, we're building a game, so let's pick games. What is the main module of the executable? Main.hs. Application directory. This is just the name of the folder. Usually we pick up the language of your executable. In this case, the three most frequent options of languages are the two official releases of Haskell, which are Haskell 98 and Haskell 2010. But we also have the option to use the GHC 2021 language, which is Haskell 2010 with a bunch of extra extensions. We are going to learn more about extensions in this lesson, but for now, let's just pick Haskell 2010. Add informative comments to each field. Usually not, but since we are learning about them, we're going to say yes. And there you go. We have our app ready to go. Let's see the files. We have a license file with the MIT license. We have our Cabal file, as you can see, is .cabal. We have the changelog, and we have an app folder that contains the main module with the main action. We also have this-new style that we can ignore because these are just build artifacts generated based on our actual source code. So the interesting part is actually this ForestGame.cabal, the Cabal file. This is the file that expresses all the details of how to build our software. So let's close this, close this. The Cabal file has the structure of keys and values similar to the YAML file. And in this case, we chose to have a bunch of descriptions. You can pause the video and read them, or just choose to generate them when you create your own project. The first one is stating the version of Cabal, then the name of our package, then the version of the package. As you can see, this version is 0.1.00. A short description of the package. We have the option to do a longer description. We choose not to. The license, MIT, the file containing the text of the license, the author, maintainer. We can also have a copyright notice. We don't. The category of the package, that's a game. The build type is simple. For now, we are going to use only simple, but you can change this in more advanced scenarios. Extra documentation, we have just the changelog. Extra source files, we don't use any. And now we have our first configuration. We always have the option to provide GHC options. The GHC, the compiler, has a bunch of flags that we can pass to improve optimization, to change the warnings, to change how the actual source code is processed. So Cabal allows us to state these options directly. This is what the GHC options stands for. And this WO that turns on warnings that indicate potentially bad code. Now this option is indented further inside these common warnings. That means that this option is part of the common warnings statement that states that we are going to create a common set of instructors called warnings, and we add all the instructions we want, in this case just one. And then we can import all these instructions inside the executables, libraries, or test suite configurations. That makes it easy to avoid repeating the same thing in all cases. Now let's see our first case, which is, I think, the only case. Let's see. Yes, our executable ForestGame. The first thing we're going to do is to import warning flags. Great. Then we are going to indicate where the file containing the main module is. In this case, because the main module is inside the main HS file, we indicate it here. Then we can indicate other modules that for now we are not doing that. Then language extensions used by all the modules in this package. We're going to see what the language extensions are in a bit, but for now we're going to ignore it. And then other libraries that our ForestGame executable depends on. In this case, we depend on the base library. We always depend on the base library. And the version of the base library depends on the version of GHC you are using. A common mistake that new Haskell developers have is to have the wrong base type. For example, when you clone a repository to start working on it, you try to compile it for the first time. It says, hey, your base is wrong. You need 4.14 and you have 4.16. Then you come here, you change this 4.16 to 14, and it breaks. That's because the base package comes with the GHC version. So if you want a different base package, you need a different GHC version. If you run GHC up, you will see which base version comes with which GHC version. Then we indicate which directories contain the source code. In this case, because we just have one directory, the app directory, we just indicate that one. And finally, the base language we're going to use. As we stated before, we are going to use Haskell 2010. And as you can see, it's not that much of a configuration once we remove the comments, but we are going to make a few changes during this lesson. Before that, we're going to learn a couple more commands. Save this. Let's open terminal. Make it a bit bigger. And now, the next command we want to learn is Cabal build. This command will try to build our executable and libraries indicated in the .cabal file. So let's run it. As you can see, it's trying to compile the ForestGame executable. After configuring and pre-processing, it starts the actual building of the executable. And to actually build the executable, the only thing it has to do is to compile and link the main file. And that's pretty much it. The ForestGame has been compiled. Of course, the ForestGame is just a single Hello Haskell put string line, so it's not very interesting right now. But now that we have it built, we can execute it using Cabal exec. Hello Haskell. Perfect. Because the development cycle needs to always build and then execute, Cabal has a handy function that does both at the same time. Cabal run. As you can see, it did the same, but in the case that we change the executable, we run Cabal run again, it detects that the source code changed and rebuilds, links, and at the end runs the program. Okay, so we have our setup ready to go. Now let's do something more interesting. We saw in the previous lesson that we built a pretty simple CLI game. We're going to copy and paste the code from that CLI game, and we're going to use Cabal to add functionality from external libraries, change how the Haskell code is interpreted, and try to make the game a bit more fun. Okay, so let's copy the source code. If you already watched the previous lesson, you should already know how all this code works. But just in case, once we finish copy and pasting, we're going to go over the whole code. So this is the main function. And now we have to copy and paste these forest level 1 and user actions move modules. We could copy and paste them inside this app directory, but instead we're going to create a new folder called source that's going to contain most of our source code. And in the app folder, we're going to leave just the main action, the entry point of our executable. This structure of having just the main here and the rest of the code here is pretty common in Haskell programs. So now inside this source, let's copy the forest levels, we have a level 1, and we have the user actions. User actions, we have battle and move. In the previous lesson, we called this attack, but I chose to call it battle now. Of course, it's still empty. And we're having a bunch of errors that we're going to solve. But first, let's go over the code. So as you can see, here we have the main function that introduces the player to the situation. It creates a game loop with the starting parameters, in this case, 10 of stamina and a level 1 forest that we import from the forest.level1 module. And then we run the game loop. If we find the exit of the forest, we print you found the exit and that's it. If we run out of stamina, we print you run out of stamina and died, and that's it. But in the case that we didn't find the exit and we still have stamina, we print the amount of stamina you have and the options you have. We get the response from the user and run the game loop again with the updated state. To update the state of the forest and stamina, we use this move function that takes the current state and the option that the player selected parsed as an available move. And this move function that comes from the actions.move has this structure. As you can see, we have 3 options of available moves: go forward, go left, and go right. And the move function that takes the current state of the forest and stamina and the available move and returns a new state of the game. In the case that founds the exit, it just returns the same, found the exit, and with the same level of stamina, so there's no change. If we chose to go left, we choose the trail of the left. If you choose to go forward, we choose the middle trail. If you choose to go right, we choose the right trail. In every time, we take the amount of stamina and subtract the amount of stamina needed to walk through that trail. And finally, we have the forest, level 1, level 2, it's empty. Just an example of a possible next step. In the level 1, we have the actual forest, which is a recursive structure, which we have the found exit constructor, and we have the trail constructor that takes the amount of stamina and the 3 possible options inside. Then we create an actual level with this structure that starts with a trail that consumes 3 of stamina and contains 3 more trails. Let's put this in the middle, make it a bit smaller. 3 more trails. The second consumes 7, it has 3 more trails, etc., etc. But at the end, we always find the exit. So the objective of the game is to find the exit before running out of stamina. If you want me to go over the code more slowly, go watch the modules lesson when we actually take all this code and separate it in all the modules we just saw. Now, in the modules lesson, we didn't have any errors, but now we're having errors in pretty much every file. And in the main, we have even 2 errors. So let's solve this. The first one says, could not find the module forest.level1. This is not a module in the current program on any known package. The problem we're having now is that we have all this source code inside the source folder, but we never told Cabal that that's where we have part of our code. So let's go to the ForestGame.cabal file, scroll to the executable ForestGame, and say, hey, if you want to build this executable, you need not only the app source directory, but also the source directory. Awesome. As you can see, the error went away, but the Haskell language server is not working because we still have more errors to solve. If we go here and hover a bit, it has a pretty cryptic error, but if we go to the forest.cabal file, we can solve this by adding the other modules included in this executable. As you recall, a few minutes ago, when we went over all these configuration options, there was a configuration called other modules that we could have used, but we didn't need to, so we removed it. Now, we can use this function, other modules, to indicate which other modules we are using in our executable. We already have this source code available because we added to the source code directory. So the only thing we have to do is to indicate the name of the modules. So to build the main function, we need the forest level 1 and user actions move modules. So let's go here and write forest.level1. And also, let's add a comma here, user.actions.move. Now that we indicated the other modules that we are using, if we save, should process, and it fixed both errors in the level 1 and in the move, but we still have these errors in the battle and level 2 modules. We're not really using them, so one option is to delete them, move to trash. That's it, one less problem to deal with. But the battle module, we will want to use them because as a homework, you will have to integrate battle to the game. In that case, you will need to add it as well, but I am going to remove it so you can do it yourself. Let's reload the window. And now we should have 0 errors. And we have, of course, the language server capabilities because everything is great. Awesome. So we have our ForestGame that we built in the modules lesson working within a Cabal package structure. Now let's take advantage of this and let's use Cabal for its main job, to resolve dependencies. Resolving dependencies by hand is cumbersome, time-consuming, and error-prone. That's why most popular programming languages have a tool to do that automatically. Let's say we want to modify our game to be more engaging. The first thing we need to do is to add randomness to it. Else, once we win one time, we can repeat the same steps and win every time. If you want to try it out yourself, now instead of running GHC and the main, etc., we can run Cabal run. It builds everything needed to run the ForestGame executable, and it runs it. You're trapped in a forest, try to escape, go forward, go left, found the exit. And now every time I run this program, I can just run it, choose the same paths, and I will always win. Kind of boring. So we want to use randomness. What do we need to do? Well, let's look for a package that provides this randomness. If we go to the Hackage repository, and we can browse packages and look for random. We have all these options. You can read this description here to have a general idea of just click here and read more. We're going to take the first one, the random packages, pseudo random number generation, perfect. This package provides pseudo random number generation, including the ability to split random number generations. It has a short explanation. And if we want to know even more about the package, oh, there's even more here. And there's also, if we click here, you will always find more documentation, no matter the package. So, how can we use this package inside our code? Well, it's super easy. We go to the ForestGame.cabal, and in build depend, we can add the name of the package we want to use, random. And that will be pretty much everything we need to do. We have, of course, the option of specifying the version. As you can see, this random package has all these versions. 1.2.1.1 is the last one, so we can just 0.1.1, the last version. The cool thing is that now that we added this single line to build depends, Cabal will figure out everything needed for us to use this module, so we can just start using it right away. Let's go to our main file and import system.random. If we go to the documentation, we can see that system.random is the module we're importing with all this documentation. If we read for a while, we will get that this random RIO function gives us a randomly generated number in a range specified by us and the type specified by us as well. So let's use this function. And now we can go here and say, okay, random, we want to generate a number between 10 and 20, for example. And we want to bind the result of running this action to the starting stamina variable. As you can see, we have an error here. This says ambiguous type variable. This is because this action doesn't know the type of the values it has to generate. These literals 10 and 20 could be integers, int, doubles, etc. One thing we could try to do is to do IO int, and that indicates that this whole expression is of type IO int. It's a bit verbose because we're indicating that this action is of type IO of something, and we already know that this is a type of IO something, but this will work for now, just for now. And now that we have this starting stamina, we can replace this hard-coded number with this starting stamina. Let's try it out. If we run Cabal run, because this is the first time we run this, it will download all the libraries needed, it will build all the modules needed, and it will run the final executable. So let's hit it. And that's it. As you can see, now that we run this, it says you have 18 of stamina. It picked a random number between 10 and 20. If we close this and we run it again, you have 11 of stamina. You have, again, 11 of stamina, 19 of stamina, etc., etc. This is great, but just to make it a bit more engaging, let's use bigger numbers to add more range and variability to our game. So instead of generating a random stamina between 10 and 20, we can do it between 10,000 and 20,000. And now we have to change the level, so it's not extremely easy to win. Pretty much with the current level, it's impossible to lose, actually. So let's make it 3,000. And there you go. Now that we have bigger numbers, it's harder to predict if you will win. If we run Cabal build, as you can see, it compiled the forest level 1 again, and the main. The other modules were the same as before, so it just ignored it. And Cabal exec, you have 70,222 of stamina. Go left, 14,000. Go right, 7,000, etc., etc. Now, the next feature to add is a battle mode. We could use this randomness to throw a dice, for example, and in every move there's the chance of encountering a golem or a troll or whatever, and have to fight them. And we can use the same randomness to assign the attack and HP of both the player and the monster, and the luck that changes in every turn of the battle. That will make it way more interesting. And on top of that, we could add the option to escape the encounter, in which you roll the dice, and if it lands favorably, you get to escape. But if you don't, you get hit by the monster, but you don't hit the monster back. Knowing all the changes that come ahead, let's learn about extensions so we can make our code more readable before adding all those features. If you developed in other mainstream languages, the concept of language extension might be foreign to you. Usually, a certain version of a language has a fixed syntax and way of working. Haskell, and in particular GHC, has an extra flexibility that allows you to change the actual language, the syntax and how it works, depending on which language extensions you use. When you activate or deactivate language extensions, the compiler changes how it interprets your source code, and in turn changes how Haskell looks like and works. This has the advantage that you can tailor the features of Haskell to your own needs, but also the disadvantage that if someone uses a set of extensions that you don't know how to use, the Haskell code will look foreign to you. This resolves eventually once you have a good idea of all the most used available extensions, but at the very beginning, it might make it difficult to understand other people's code. Up until now, we've been using Haskell 2010. But as a way of introducing you to extensions, let's use a couple of them to change how our code looks like. One thing that bothers me is the numbers. When the numbers get bigger, it's harder to know if this, for example, is 1,000 or 10,000, just with a quick glance. One solution to this is to use numeric underscores. For example, if we put something like this, we know that that's a 3,000. If we put something like this, we know that that's a 10,000, 4,000, etc. This is great, but there's an error, like it's not an actual number. But as you can see, the language server already knows that there's a language extension called NumericUnderscores that allows us to put underscores in integer literals. Perfect. So if we accept this add numeric underscore quick fix, we see that the errors go away. And if we go to the top of the file, we see a pragma. This is a pragma. Pragmas take the form of the type of pragma and specific thing the pragma does. This type of pragma could be here language, that indicates we are activating a language extension, in this case numeric underscores. But it could also be, for example, options GHC, and we could put here the WL option. And when GHC compiles, it will use the WL flag only for this file and not the whole thing like we did in the .cabal. But for now, we're going to use just the language pragma that activates a language extension, in this case, NumericUnderscores. And now we have these hints that says, hey, if you are using NumericUnderscores, why not use 7_000 instead of 7000? And yes, we can apply the hints to this number only or to all the numbers. If we click here, didn't work, so let's do it by hand. Perfect. And now if we go to the main file, we don't have the warning here because we didn't activate the extension here, but we can activate the extension in this file as well. If we do this, and there you go, we have NumericUnderscores. We change how the compiler interprets the code to make it more readable to us. Another thing we could do is to change how we indicate the types of function parameters. Here we're indicating that the whole expression random RIO with the range is of type IO int, but what we actually want to do is to indicate that the random RIO returns an int. So for that, we could add the TypeApplications language extension. If we come here and we search for type, as we can see here, the type application extension allows you to use visible type application expressions. For example, we can read the string 5 and indicate that is of type int. With this add int, we are specifying that we want read to return an int. So if we come here and instead of specifying the type of the whole expression, we can just say here type int. There you go. We are saying that these numbers are of type int. And down here, we can change the select move of type available move. We can move. We can say that the read that takes the value select move should return a type available moves. If we try to use it again, let's kill that, clear, Cabal run. It recompiles everything and it still works same as before. Now the actual source code changed here, and here, etc. But the final result didn't. So as you can see, we can use it same as before. These are just small, simple examples about how pragmas, which are these tags at the top of the file, and language extensions that are these specifically the language pragma, work to modify how the Haskell compiler interprets our source code. Of course, there are more interesting and more useful language extensions that you will pick up in time when you need to. In this course, we're going to use mostly the standard language with one or two extensions now and then, and we will explain those in time. Now, before you go to find a job at Epic Games to build the next Fortnite, let's talk about the homework. The first stage of the homework is to fix the Cabal file. I'm going to remove a couple of key parts, and you'll have to use either your memory or the documentation to restore it in a way that it can compile your program. As you can see here, I don't have anymore the numeric underscore language extension, but I do have the underscores. That's because I modified the Cabal file to activate the extension for all modules used by my executable. So you have to use the documentation to know how to do that and modify it in a way that you don't need to activate the extension in any file. Then the fun part starts. The bulk of the homework is to create a single function that is called battle. As you can see right here, I modify, let me make this bigger. I modified the game loop function, and instead of running the loop as before, I put it inside a let binding called continue loop, and I draw a random number called battle dice that can be any number between 0 and 3. And then I say, in the case that the battle dice is 2, start a battle. And this battle is an IO function that returns a boolean. In the case that we win the battle versus some monster, it will return true. If we lose, it will return false. So here in the last line of the do block, we check if it's true, then continue the loop. That means we won, so we can keep walking down the forest. Else, return unit, so the program stops. And there's also the more likely possibility that we draw a number that is not 2, 0, 1, or 3. And in that case, we ignore the number and just continue the loop without getting into a fight. I'm going to show you how the final game should look like to make it easier for you when coding it. So we start with Cabal run, and says you're trapped in a forest. You have this much of stamina, so let's go forward, go left. As you can see, no battles until now. Go right. I now found the exit. In this case, it was a beautiful path with no monsters. Let's try again. And this time we found a golem. As you can see, we have two actions to choose from. Should we fight or run away? And to make that decision, we have the stats of both ourselves and the golem. The golem has 46 health points and 4 points of attack. And we have 59 health points and 7 of attack. It sounds like we will win for sure, but don't get mistaken. There's a random luck with each attack that can make an attack deal twice or 3 times the damage. So if we have bad luck, the golem can kill us. Let's try fight once and see what we do next. Nice, we dealt a lot of damage to the golem, so let's keep fighting. Woof, 11, nice, and we still have 35, so... And we won the battle, awesome. And because we won the battle, we can keep going through the forest. Let's go left one more time, go right. And no more golems, it seems. Go left, and we found the exit. We won. Awesome. Now let's try. As a final example, let's see what happens if we try to run away. In this case, we have more health and more attack of the golem, so if I were playing the game, I might prefer to fight, but as an example, let's just try to run away. I failed to run away and the golem hit me. The difference between a fight and running away is that the golem will still hit you if you fail to run away. And the value that decides if you fail or succeed at running away is a random value, same as the one we use to enter the battle. Let's try to run away again. Run. And it hit me again. And I managed to run away. And I will keep playing. Perfect. So that's how the game should look like after you finish your homework. And as an extra, I'm not going to show you the whole battle file, but I will show you the language extensions we are using. You don't need to use them, but I will ask you to practice looking around the documentation and learning about new language extensions. As you can see, in the battle, we have the type applications we used before, but now we have two new language extensions, the name field puns and the record wildcards. Part of the homework is to learn what these do and use them effectively in your code. To make this, you don't need to know anything we didn't cover so far. So try to not get frustrated and just build a small function that does part of what you want to do and then start combining more functions or making the function bigger and bigger until you have the whole functionality of the battle. So make sure to do this homework and I will see you in the next one.